Hello everybody, welcome to Math 324. My name is Lucas Braun and I'll be your instructor this quarter. This is an unusual quarter thanks to the coronavirus. I've taught this class several times at UW, but this will be my first time teaching it online. So I'm counting on your help and your feedback to make this, to make the course as good as it can be. Course information is available on the course website, which you can find from my own website. So you can find that by either Googling Lucas Braun UW or by just going to the page, the red link on the slide. So on this website, you'll see, in detail information about course organization. We'll also have the first Zoom meeting. So I'll also hold Zoom office hours, so virtual office hours. And then, of course, during those, we can talk about this. We can talk about the course organization. But today I want to just start giving the lecture and discussing the mathematics. But before I jump into that, let me just make a few remarks about the course organization. So first of all, we'll have pre-recorded, my initial plan is to have pre-recorded video lectures rather than in-person video conferences for lectures. So the lectures will be recorded and distributed using Panapto. So office hours, as I mentioned a couple minutes ago, will be virtual using Zoom. My initial plan is to hold the office hours at the times where the regular lectures would meet. So that would be from Monday, Wednesday, and Friday from 9:30 to 10:20. Well, except that I'm going to do 2 office hours a week, so maybe we'll just stick to Monday and Wednesday. For precise details, please refer to the course website. If some of you are not in Seattle and the time zone just doesn't work for you, maybe we can change one of the office hours to a different time to accommodate the needs of different students. So this is something I hope to perhaps improve throughout the quarter, but the initial plan is to have the meetings at the time where the lectures would normally meet. Next, homework in our class will be distributed and collected using WebAssign. So normally I tell you to just walk to the UW bookstore and buy an access code, but this quarter you can't, maybe you can't, or you probably shouldn't go to the bookstore to buy the access code. So I'll just remark that you can buy the access code online. So you just receive a message with the code. You don't have to get a piece of paper with it. So please check the course website for information on how to do that. So some people ask whether they should buy the book, and my answer is that the lecture notes. So I'll be distributing lecture notes on the course website. They should be up by the time you guys access the page. So the lecture notes should be the main reading material. They're more concise than the book, So the book is by no means necessary. But given that you're learning online this quarter, maybe you want to buy it this quarter. So normally I would say you don't have to buy it. Just checking things up. So the WebAssign access comes with an electronic version of the book. Normally I would just say the ebook is enough. But maybe this quarter you might want to have a physical copy too. So you can interact with the book more. But it's up to you. And finally, our course will have exams. There'll be, regular exams. But you'll do them remotely. You'll do them from home. So the exams will be distributed. So you'll take exams using this website called Gradescope. So the way Gradescope works is at the time. So I'll put out the exams at a particular time later in the quarter. I'll put them out, and then you access the exam, access Gradescope, and then once you start looking at the exam, you have 1 hour or maybe a little bit more time to work through it. And as you finish one of the problems, you'll do that in a separate piece of paper, in your own home, and then you take a picture of the paper and you just upload that as your answer. So, so I guess the best way to see, so there is already a sample midterm 1 on Gradescope, and I encourage you guys to check that and see for yourselves how it's going to work. Okay, so so let's get to the materials of this course. So I'll begin. So the course before the first midterm, we'll discuss double integrals and triple integrals and changes of coordinates, things like cylindrical coordinates, spherical coordinates, and applications of these integrals in physics. So what they're good for. Then in the second part of the course and third parts of the course, we will learn about vector calculus. So the main objects will be vector fields. So they're like functions, but instead of getting a number for each point in space, you get a vector for each point in space. And then we'll learn how to differentiate vector fields. So we'll learn about divergence and curl, which are kinds of derivatives. We'll learn about what these things mean for in fluid mechanics and electromagnetism. And we'll learn how to integrate vector fields over curves and surfaces and what that means in physical terms. So in the second midterm, we'll cover 2D vector calculus, and in the final, we'll cover 3D vector calculus. So that's the rough outline of the course. So the topic of today is double integrals. So let's jump to that. Okay, so before we look at double integrals, so this is a recap from 126. It'll be brief, but because these integrals are so important for the rest of the class, I think it's worth making sure that everybody's on the same page. So I'll just start from zero, but I'll be kind of brief, but kind of fast. So here's a recap of double integrals. So the motivation for a double integral is just like the motivation, the geometric interpretation for double integral is pretty much the same as a very close analog to the interpretation of a single integral. So recall that if you have a function of a single integral, of a single variable, so let me draw a graph of the function to illustrate this. So I have a function f of x, and the graph is going to be this curve where in the y-x plane, where y is equal to f of x. So I have a function f of x, the integral of f of x dx over an interval ab. So this is, you look at the values of the function between a and b. So this integral is just the area below the graph. And above and over, so the graph y equals f of x, and over the interval ab. All right. So now let's look at what double integrals are. So if I have, when I do a double integral, I do it over, instead of an interval AB in the real line, I do a double integral over a region of the xy plane, and I integrate a function, f of xy, with respect to dA. Okay, so here's the picture for this integral. We're looking at not the area below a graph, but the volume below a graph. So let's see what this looks like. So the graph, the graph of a function of two variables is gonna have the equation z equals f of xy, right? So the original variables are x and y. You add in a new variable z, and you say that new variable is equal to f of the old two variables. The graph is going to be a 2D shape, something like this. And we're looking at the values of f over a region R of the xy plane. So let me draw this region R of the xy plane here. Right, and the double integral of f over this region R is just the volume below the graph. And over R, over the region R. Right, so it's this, it's the volume here that's below this graph and above the region R. So this interpretation, I think, is geometrically clear. There are a few caveats. So first, if the function, it's really a signed volume, because if the function were below the xy plane, then we'd be talking about the volume above the graph and below the xy plane. So if the function were really I should say the signed volume between the graph and the xy plane. But this caveat was already present in the 1D case, so I think because we're used to that this shouldn't scare us too much. So this is how this is the quick one phrase definition of the double integral. So there's another definition using in terms of Riemann sums, and this is really the definition you want to know because it's the definition that's closest to how the integral appears in most applications. So here's the definition using Riemann sums. So first, what's a Riemann sum? So a Riemann sum has two ingredients. So first, let me draw a region of the xy plane, so I can draw these ingredients for you. So the region, let's say this is a region R, the xy plane. Okay, so a Riemann sum has two ingredients. The first is a partitioning of the region R. So I'm just going to break R into a bunch of subregions, smaller subregions. Okay. Now I'm going to pay attention to one of these, and in each of these subregions I'm going to pick a point. So this first subregion, this subregion that I selected, let me say it's the ith one. So we have little region number 1, little region number 2, little region number all the way up to a billion. This is the ith one. The area of this ith one is going to be denoted delta AI, and we're also going to pick inside each little region, each subregion, a point, and that point will have coordinates xi and yi. Okay, so the point that I marked over there has coordinates xi and yi. Right, there's x1, y1, x2, y2, and so on. So if you give me a partition and you give me a sample point inside each subregion of R in this partition, in each piece of R in this partition, the Riemann sum is this expression over here. It's sum over each little piece of the region. So here's a sum of the I that tells me which piece of the region I'm in, and I'm summing over all pieces of this that make up this region. It's the sum of the value of the function at the sample point times the area of that piece of the region. So this sort of sum is called a Riemann sum. And so let's see what this is doing. So if I select a small square in my region. A small region, a small piece of R, and then I pick a point in there. So here's f of that point up here. If I multiply the area of that base, the area delta AI, by f, I'm getting the height of this column over here. The little column, right? So this is the height. So this column, it's almost the volume below the graph and above this area delta AI. In fact, if delta AI, if the size of these little squares is really small, if the size of these little pieces are all very small, then the value of these sums approaches the integral. So the limit as the size of the subdivisions becomes increasingly small, the limit of these sums, when you take very fine subdivisions, this is equal to the double integral of f over r. So, so this is the Riemann sums approach to double integrals rather than a geometric approach to double integrals. So what this is saying is that one way to think about the double integral is it's approximately the number you get by breaking your region into very, very small pieces, picking a sample point in each piece, multiplying the value of the function, multiplying the area of each piece by f, the value of f at that sample point, and then adding everything up. So later in the next lecture, I'll tell you about applications of double integrals, and you'll see that this point of view is really useful there. So for now, please take my word that it's going to be useful. Okay, now let me just copy this picture on the left because I want to make a few remarks about it. So copy. So next up, let's look at how we, instead of conceptualize double integrals, how we actually compute these things. So let me show you how. So I'm going to do this. I'm going to pick a point in the x-axis. Pick a value of x0, say, and let s0, let s of x0 be the area of the slice of this volume by a plane parallel to the YZ plane. Okay, so here's what I'm going to do. I'm going to take a vertical plane, a copy of the YZ plane, bring that, so look at the copy of the YZ plane that passes through, that has x equal to x0 rather than x equal to 0. And you use that plane to slice this volume, this solid region between the xy plane and the graph. Okay, so this is, if I slice it, I'm going to get this 2D slab, this portion of this flat shape that I'm drawing in red. So here, so I want to indicate it's a 2D shape, so I'm drawing some vertical lines to indicate that. Okay. Now, here's a cool observation. Namely, so if we multiply the area of this slice, so if we multiply s of x0 by delta x, by a number delta x, what I'm doing in effect is, so I'm multiplying the area of this slice by delta x. The number I get is the sum of the volumes of a bunch of these towers, a bunch of these little towers. So it's it's like I have a column in the xy plane, and I'm looking at the volume between this thin column in the xy plane and below the graph and over this thin column. So from this point of view, we can see that the volume below the graph, so the double integral is equal to the double integral of f over r is equal to the integral of this s of x times dx. Right, because s of x is the area of the slice, and multiply by dx, you give it a little thickness, and then you integrate from the smallest value of x in the picture, so that's here, x min, to the maximum value of x in the picture, which is here, x max. Right, but the conclusion is that the volume we're interested in can be computed in terms of a single integral of a certain function, s of x, right? The area of this red slice changes as x changes. Now, that area of the slice can itself be computed as an integral. So s of x0 is equal to, let me just say s of x. So s of x, the area of the slice where the x-coordinate has a fixed value. So the area of this red slice is going to be an integral in y. You see y is increasing. Let me draw the picture. Let me draw r on the side. Okay, let me say a region looks like this. And then x, as I said, is going to be an integral like this. Right, if I fix an intermediate value of x here, and then the area of the red slice is going to, so the red slice lives over this vertical line that I just drew. And then to get the volume of the whole region, I have to move x from the minimum value to some minimum value, from some minimum value to some maximum value. And to get the area of the slice of the region, I should integrate over this red line segment. And the integral over the red line segment is going to go from here to here. So y starts at some minimum value that can depend on what x I fixed. And that's going to stop at some max that also depends on what x I fixed. So s of x goes from, is an integral in y, where the bounds depend on the value of x that I fixed, and then you're integrating f. So the input, the x-coordinate is fixed, but on this red line segment, y is changing, and you integrate that with respect to y. So in conclusion, we get Fubini's theorem, which tells us how we can compute integrals, double integrals. So according to Fubini's theorem, the double integral of a function of two variables over a region R with respect to area, the only sort of double integral we do, is equal to two iterated integrals. So first you do an integral where in x, where x goes from some minimum to the maximum value of x at any point in the region R, and then you integrate with respect to y. So then you're integrating the function s of x, but that function is itself an integral. So let me just write that integral here. Integral from y min to y max of x, and then you integrate the function f of xy. So the inside integral is with respect to dy, the outside integral with respect to dx. So here the thing I have in red brackets and square brackets is the function I was calling s of x before. So we know how to compute single integrals analytically, using the fundamental theorem of calculus. And now Fubini's theorem tells me that if I know how to compute single integrals, I can also compute double integrals. So this is going to be your bread and butter throughout the whole course. Let me put this expression, this formula in a box. So I should note that, so Fubini's theorem, so this is a formula. The precise conditions, so Fubini's theorem, if you look it up on Wikipedia, is actually going to tell you exactly for what kinds of functions this formula is true. In this class, let me just, our point of view is that so for all ordinary functions you find in engineering, almost all functions you find in engineering and physics, the formula will be true. So you should always act, so from an applied math perspective, you should always just use this, use the formula, and if you find a contradiction, maybe it could come from the fact that the formula doesn't apply in your case, but that's extremely unlikely. Okay, so now let me just check my notes on my phone because I didn't print them. Yes, so we're ready for our example. Well, the only thing I didn't write here that is on my notes is that this integral we have on the right is called an iterated integral. So let's do an example. So here's how Fubini's theorem works in practice. So we're going to do the double integral of the function x plus 2y. And the region is going to be the region bounded by two parabolas. So in this class, we should draw everything very carefully. So the region will be bounded by two parabolas. The first parabola is y equals 2x squared. So it grows, so that's our first parabola. The other parabola is a little bit wider. It grows more slowly than this one. So the function grows more slowly than this one, but it has a head start. So the other parabola is y, let me draw it like this. This one is y equals x squared plus 1. And our region is just this region between the two. So I'll just call it R like this. Okay. So our job will be to compute the double integral over R of f of x, y with respect to dA. So to do that integral, we're going to we have to understand this picture really well. So first, I can tell you in advance that we're going to need these 2 points. So the points where these two parabolas meet. So let's see if we can figure out where these what these 2 points are. So the set of blue points, the blue curve is a set of points where y is equal to 2x squared. The red curve is a set of points where y is equal to x squared plus 1. So the 2 black points, the 2 marked points, are on both curves. So on those points, both equations are true, right? So on those 2 points, the 2 equations are true. So this means on these points, for example, here, I know that 2x squared, that's y, that's also x squared plus 1, and therefore, this tells me that x squared, so just cancel the 2 with the x squared on the other side, x squared is 1, therefore x is plus or minus 1. So So from this observation, I get that x is here is +1, and here it's -1. Okay, how about y? Well, y on both points, it's y squared plus, it's x squared plus 1, that's 2, or 2 times plus or minus 1 squared, that's also 2. So this height is 2 for both points. All right, so with this information, we can set up the integral. So the double integral of over this region R between the two parabolas of the function x plus, what was it, x plus 2y. That's the integral for x going from, so the minimum value of x in this whole picture is -1. The maximum value of x in this whole picture is +1. So let me just write that. X goes from -1 to +1. And then there's an integral in y. So the inside integral is really a collection of integrals. You're doing one for each intermediate value of x. Right, so you're doing the inside integral of this red segment, and y is increasing in this integral from the blue parabola to the red parabola. So on the blue parabola, y is equal to 2x squared. On the red parabola, y is equal to x squared plus 1. Right, so the lower bound for y on this segment, it depends on x. Right, the lower bound is the value of y in the lower parabola, and the blue parabola, that's 2x squared. So let me just do that, 2x squared, and the upper bound for y, that's the value of y in the red parabola, that's x squared plus 1. Then I'm integrating the function x plus 2y dy dx. Okay, now let's evaluate these two integrals. So when we do the inside integral, we should remember that x is held at some number between -1 and +1, right? Could be 0, could be half, minus half. So x is some fixed constant, and y is the function we're integrating, is the variable we're integrating. So let me just repeat the x integral, that's x from -1 to +1. And then we're integrating x plus 2y dy. The primitive, so the integral of x, a constant times dy, is just that same constant times y, plus the integral of 2y dy is, with respect to y, is just y squared. And then we evaluate that with y between 2x squared and x squared plus 1. And the end result is going to be integrated with respect to x. Now let's see what this function of x we're integrating. So let's just evaluate this inner term. So we get x times y. At the top, it's x squared plus 1 plus y squared, so x squared plus 1 squared, minus x times y at the bottom, that's 2x squared, so that's minus 2x cubed, minus the value of the bottom squared, y, so minus 4 times x to the 4th power. So if I to evaluate this polynomial, I'll just collect terms. So first, the coefficient, what's the coefficient of, so the highest possible power of x in this expression is 4. The coefficient, so there is no x to the 4th in the first term, there is just 1 x to the 4th in the second term, nothing in the third, and minus 4 in the second, so that's minus 3 times x to the 4th. Now let's look at the cubed coefficient. There is 1 here, 0 here, minus 2 here, 0 here. So that's 1 minus 2. Result is minus 1. Let's look at the coefficient of x squared. So there is no coefficient of x squared here. Here there is, that's 2x squared. There are 2x squared in the second term, 0 in the third, 0 in the fourth. So it's just 2 times x squared. Let me just give myself some room here. Plus 2 times x squared. plus, let's see, the coefficient of x here is 1, 0, 0, 0, so plus x, plus the coefficient of the constant. So what's the constant term? There's nothing here. There's the constant is 1 in the second term, nothing here, nothing here. So the overall constant is 1. And so this integral is the integral for x going from -1 to 1 of minus 3x to the fourth minus x cubed plus 2x squared plus x plus 1 dx. This evaluates to, so let's do this integral together. So it's minus 3 times x to the fourth, it integrates to x to the fifth over 5, minus integral of x cubed is x to the fourth over 4, plus integral of 2 times the integral of x squared, that's x cubed over 3, plus integral of x, that's x squared over 2, plus integral of 1, that's x, evaluated between -1 and 1. So, okay, now I think I did a lot of the grunt work for you guys. The rest part is just plug in 1 in this expression, and then plug in -1 and subtract, and the result you get, according to my notes, is 32 over 15. So I'll just put a box around this and be happy that I was able to complete the line integral. Whew. Okay, so that was a lot of work. This is what I had to say in this first lecture. You guys already have enough that you can enough information to get started on the web assign homework that's due this Friday. So by all means do. And so that's it. Thanks for listening. I'll see you guys next time.